we have the answer. Like, we have the answer. When you compress it, the temperature rises. But the question is, why? And that was also explained, right? When the piston is moving, the atoms that are hitting it are getting rebound by like a greater velocity. When I first heard this, like I was a little confused. Why would it come back with the more velocity? But if you have a good physics answer to it, then conceptualization, then it's very easy to visualize that. Tiffany, were you going to say something or ask something? Okay. So just imagine like this. I imagined like this. If everything is stopped, like if you have a molecule that is just sitting there, and if you have a moving piston, what will it do to the velocity of this thing? It's going to increase it. So that's what it's doing, basically. So when it can add that its own velocity, so it's basically adding its own velocity into the molecules. So the same thing will happen when it rebounds. So if the piston was static, it would have rebound with the same velocity. Go 10 units on this side, come 10 units back. That's what happens. Like, so if you bang this, it's no friction, blah, 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 and all those like ideal situations. But if that thing is moving in, is the relative velocity it's the relative velocity concept. The velocity gets added. So that's what is happening. And when the velocity gets added due to compression, when you compress it, you're moving faster, and then the temperature increasing. It's an important concept. Like when you compress a gas, it gets warmer. What's the opposite of it? Expand the gas, but slowly. And I will tell the opposite is expand, but slow. The temperature is going to drop. Okay? Just the opposite concept. It's easy. I'll tell you about this slow thing in thermodynamics. Like there is a concept in which we will try and understand the difference between a slow process and a fast process, and how these are two very different things in thermodynamics. It's the way that we do any, you might have heard isothermal compression, expansion, whatever. So the slow expansion of this gas will again decrease the temperature, because of, if you understand this, it's just the opposite of this. Okay? Any doubts? Nope? Okay. So let's now move on to the concept of atomic structure. Okay? We'll start very basic on this concept. We'll just assume that the old ways of thinking, like the classical ways in which you have a nucleus in the middle, then you have the orbits, things like that. We start from there, because if we understand that concept clearly and it's easy to understand, we'll be able to like understand most of the chemistry concepts until a point when this cannot explain the ideas, then we'll shift the main core principles. But for now, let's assume that the atom is made up of what? You know?
Protons and neutrons.
Protons, neutrons, electrons. Positive charge, negative charge, no charge, or no charge. Now, what is the unit of charge? The SI unit of charge. Like the SI unit of length is meter. What's the SI unit of charge? Coulomb, right? Yeah. Sorry, so Coulomb. So this doesn't mean that the charge is some coulombs, okay? Some small coulombic charge exists on one proton. Some small, equal in amount, equal in magnitude charge exists in electrons also, okay? Now let's not get into what exactly that value is because we are not using it for our calculations. Whatever that is, let's assume that is 1 unit charge, 1 unit. But we'll just say 1 unit positive charge exists on a proton, 1 unit equally, like that exact same unit, exists on electrons. Okay? Similarly, there exists, this has some mass, right? This has some mass, and this has some mass, grams. Which one is the lightest? The electrons are the lightest. So this one will have the least, so least. These are equal, right? This and this is equal, but the electrons are the least heavy. What about these two? Are they equal? They're about equal, and for our purposes we'll assume they're almost equal, but which is the heaviest one? Neutrons are the heaviest ones. So neutrons are the heaviest ones. Now this becomes important when we try to understand why the nucleus is stable. Now what exists in the nucleus? What do we have in the nucleus? The protons and the neutrons. They together form the nucleus, they form the core of an atom. So something like this. Okay, and then the electrons are there in, so this is the nucleus. The things that are there in the nucleus are called nucleons. So protons and neutrons, they are also called nucleons, just another term. These are orbits. This is the first orbit, this is the second orbit. The first orbit is called the K, the second is called the L, M, and so on and so forth. Okay, why K? I have no idea. It started with a K, we are going with it. There will be many things, there will be many terms that we just don't know how it started, but we are still sticking to it, no logical explanation. Okay, because these things were happening way back when people were not probably sitting together and thinking about like nomenclatures and stuff like that. So we are stuck with it. So this is the K shell, L and M and so on and so forth, so increasing. So this is like the planetary model, right? So it looks like the solar system with the sun in the center. Okay, these are the nucleus. The nucleus has the protons and the neutrons. Can anyone tell me plus 1 coulomb charge and minus 1 coulomb charge, which is greater than which? Which is more? Like 5 meters is greater than 2 meters in a similar way, plus 1 coulomb charge and a minus 1 coulomb charge, which is greater? They're equal. The minus and the plus is not on a number line concept. It's just a way of differentiating between the two types of charges. It's like poles, like a north pole and a south pole. Which is bigger? None of them. Like they are equal. It's just a convention. So not always a plus and a minus means that the minus 5 unit of something is less than the plus 5 units of something else. Keep in mind, because this plus and minus convention keeps on popping in thermodynamics as well. In exothermic process, we'll see that when heat is released, it has a negative unit. When heat is absorbed, it has a positive unit. That does not mean that the plus 5 joule, and heat is measured in joule because joule is the unit of energy, it does not mean that plus 5 joule is greater than minus 5 joule. It doesn't make sense. It's just a convention of noting that these two different things have different processes. And here, this just means we have two flavors of an ice cream. It's just like that. Nothing is greater. You might like one more than the other, but it's your liking. It doesn't have any canonical advantage over the other. Okay, so the nucleus. Then you have the orbits, and the electrons go in the orbits. The nucleus stays intact. We were talking about the weight because we will understand this in isotope geochemistry as well, that the nucleus is heavy because most of the mass that is there is in the nucleus, right? Because electrons have really less mass. So the most of the mass that exists in an atom is in the nucleus, and that gives and that is a stable part. The nucleus, when you're doing normal chemistry, the nucleus does not change. It's important to know, and that's why I will does not change. But the thing is, when does it not change? During normal chemical reactions, it does not change. Nuclear reactions, the nucleus changes. And one nucleus goes to another nucleus. Why? Why does anything happen? Why does anything happen?
Become more stable.
Exactly. So an unstable nucleus goes to a stable nucleus by doing what? How can you become more stable?
Take an electron.
Lose your energy.
You reduce the energy. That's it. And to do that, they might be doing other things, but on a big picture, you just have to release the energy. And how will a nucleus release energy? How will it do it? Now, it's a tricky question. There's a famous equation associated with it. Mass and energy together, famous equation. So that is the nucleus part, right? So when a nucleus reduces its mass, that mass gets converted into energy, and that energy is released. You harness that energy to do good things, bad things, whatever. That is the nuclear energy. That is fission, fusion, whatever, radiation, fission, fusion, all these things are nuclear chemistry. But when we are not in the realm of nuclear chemistry, the nucleus does not change. And the people in the past did not know this, and that's why they were trying alchemy. What they were trying to do is convert anything into gold. So gold has a nucleus, right? Gold has a set nucleus, and that's what we'll see. Now, we'll go to alchemy in just a bit. If the nucleus does not change ever, except for nuclear reactions, what changes? What is happening when a chemical change is happening? What's actually happening? If the nucleus is intact, what is changing? What remains?
The electron.
Yes, the electrons. Electrons are getting out in whatever. And that too, most of this exchange, gain of electrons, loss of electrons, all this exchange is happening just from the outermost shell. Just from the outermost shell, which we call the valence shell. There comes the term valency, the amount of electrons lost, gained, things like that. Okay, there comes the term valency. Now, all these things, there is the rest of this The kernel, it's a term that I use, is the nucleus plus all the other electrons, and just the valence shell is left. So because all the magic is essentially happening in the valence shell, let's focus on the valence shell and that's it. Okay? And to understand what is happening, so to understand this, we need to understand which electrons are actually there in the valence shell. To do that, we have to come up with a system to know which electrons are going to which shell. So what's the configurations of these electrons in the shell? So electronic configuration. A way to find out essentially the valence shell. The entire periodic table is basically, you can understand the entire periodic table if you understand electronic configuration. Because the different groups, it's a periodic table. So we'll do this periodic table. But I'm getting ahead of myself, but since you guys probably have some ideas, the different groups are basically telling you the different valencies. So when you have the first group, the alkali metals, and what are the things in the alkali metal? So this is group 1. Group 2 is there is some similarity. So the elements in the same group will have the same outer shell electronic configuration. In the case of first group, it's easy. First group means the number of outermost electrons is 1. Second group, outermost electrons 2, and so on and so forth. There will come, like group 16 doesn't have 16 electrons, is 16 minus 8. So when you go to the other part, so there is this 2, and there is this middle one, and there is this 6. All these things are connected to the electronic configuration. And these 2, 6, and 10, all these things are connected to SPDF. The people who have learned about these things, you know that the s orbital has 2 subshells, and those 2 subshells are filling in here, and that's why we have the s block elements. And then the p block is the p orbital is getting filled up, and there are 6 electrons there are 3 subshells. Each subshells can have 2 electrons, and then you have 6 electrons to fill up. So in the p block, which is, so s block is here, the p block is here, 6 electrons, so 6 groups, 1 for each electron that is getting filled in. So D, how many? 10. Because there are 5 subshells in D, and each subshell has 2 electrons, so 10. What is the F? 14. So 1 subshell, 3 subshell, 5 subshells, 7 subshells. S block 2, P block 6, D block 10, and F block 14. It's not random. And all these things are very methodically placed. And all this ties to what? Electronic configuration. So we'll first start with electronic configuration and then move to the periodic table and see how the electronic configuration connects to the periodic table, right? Okay. Now once we know this, this is like a general, like a big picture concept, but an important thing that you might already know is the concept of atomic number. Can anyone tell me what is atomic number?
Like how much weight's in the, or that's either it's the number of protons or it's the number like of protons and neutrons.
Class, take a vote. Is it, who thinks it's a number of protons? Or the mass? Thinks it's the mass.
It's the molecular weight.
But that's the top number, so that's the number of protons.
Yes, and we are not dealing with molecules yet. We are still in atoms, single. So we'll go to molecules, and so we have to go from atomic structure to periodic properties, which deals with the periodic properties of the elements in the periodic table. Then we'll go to bonding. We'll bring two atoms together, we'll bond them and form the molecules. Okay. Now, we have atomic number and mass number, essentially. Now, since we just have protons, neutrons, and electrons, let's assume we have element X. Okay? We will assign two numbers to the element X. One will be a atomic number and one will be a mass number. So the atomic number is given by Z and the mass number is given by A, which is stupid, but I mean, that's what it is. I can change it in this class, but when you go out, it still remains. This is the mass number, this is the atomic number. Now, atomic number is just the number of protons in any atom. It's just the number of protons. Okay? So this is equal to the number of protons. Now, what is the charge on an atom?
I don't know.
Sorry?
I don't know. Sorry.
Isn't it like 0 because the protons and electrons are equal?
Yeah. It is 0. So the charge on an atom is 0 because the number of protons is equal to the number of neutrons. So this is equal to the number of electrons, but this only holds true in a neutral atom. Okay, this is only holds true in a neutral atom. When an atom gets a charge on it, that means, say, you have heard about sodium cation, Na+. What does that mean?
That means that it gave away an electron.
Or gained a proton, right? Isn't it? How can you get a positive charge? You can lose an electron or gain a proton, right? Or not right? Why?
Because I feel like the protons, that's like a fixed number.
Yes.
Because once you add another one, it changes the number. It's a different number.
The nucleus is fixed. You cannot touch the number of protons. You cannot. The number of protons is fixed. You can only increase. Na plus is Na plus because it lost an electron. It does not mean that it gained a proton. Same for Cl minus. Cl minus doesn't mean that it lost a proton. It means it gained an electron. So anything that plus, minus, whatever, it is only because either a proton is getting lost. So if you lose, electron is getting lost. So if you lose an electron, you became a plus ion. This is a cation. And if you gain an electron, you became an anion. Right? So negatively charged ions. Okay. So in here, we will never say that the atomic number is the number of electrons, because what is the atomic number of Na plus?
The atomic what?
The atomic number of Na plus, or hydrogen plus. Say you have H plus. What is the atomic number of hydrogen? And H plus? It is still 1 because the number of proton is still 1. So atomic number is that identity that does not change. It's a very strongly bound identity. It will not change. So that is why we refer to this atomic number as one of the important ways of distinguishing. So when I say if the atomic number of sodium is 11, it's going to stay 11. It's very fixed. It cannot be anything else. But we'll see that the mass number is not that unique property, because two different elements can have the same mass number. Now, before going to what mass number is, so we understood what atomic number is, right? atomic number is just the number of protons in an atom. Okay? Let me draw something here. Or probably I'll just draw this thing. So you have an element atomic number 1, 2, and so on and so forth. The mass number is just the number of neutrons plus the number of protons, which is there in the nucleus. Okay, protons plus neutrons. So this is just P. This is P plus N. I want you guys to fill this up and then add on a column of proton, neutron, and electron. Just do it for, I know it's very easy, just do it.